Right, you can hear me, right?
Yeah. Yeah.
Good. All right. So let's continue then. And so you may notice that the class is called Modern Physics, and I'm talking about mechanics all the time. All right. Well, first of all, it's going to change in a couple of lectures, and second, what I find really illuminating about that modern physics is that a lot of concepts which can be easily understood in mechanics, in simple mechanics, simple things of like things moving around, they actually translate onto much more complicated stories on in sort of higher level physics, and I think it's more essential to understand how it all works than to actually throw a bunch of examples on you that I will not be able to explain in any depth anyway, and you will not learn anything except maybe some keywords, which is actually good, but you can do it on Wikipedia if you want. But just read the book, whatever. I'm really trying to explain the concepts which are used all the time, and it turns out that it's only very few ideas, which very profound ideas, which are used in physics in order to move forward. I mean, they appear once in a while, but not that often. And those ideas which I actually trying to explain. And today, what I'm going to spend most of the time on is what is one of the most profound ideas in physics which we know of. It's called spontaneous symmetry breaking, and it's pretty much described almost every phase transition which you have. And phase transitions are very important in understanding everything about our world. And I'll talk about that later, because before that, I want to come back and say something about those oscillations again, and about the role of dissipation and noise in the systems. So you may think that the dissipation and noise, especially noise, complicate problems a lot, right? So noise means that there is some forces which are like jiggling our system all the time, no matter what it is. I mean, you can think about some oscillator, or I don't know, some material which has to be at some state, and there is some noises which always shake it a little bit here and there. There is also a dissipation, which, as I explained before, the dissipation comes from coupling of some system which you're interested in into a much larger system, which in many cases is called bath, thermal bath, or something like that. So it means that it's huge, but it's huge, but we are not interested in what's going on there. We're interested in what's going on with our system, and that coupling, the first in first approximations, that coupling of our system with that huge bath can be described by simple dissipation. And I use that dissipation. I wrote that I don't know, x double dot plus 2 gamma x dot plus omega squared x, omega naught squared x equals 0. That my oscillator with dissipation, and that term is a dissipation. And I was talking about the time reversibility and how it's taken care of by a coupling with a huge system. There is also one more point here which I didn't mention, but it's quite important for the calculations. It's that the dissipation is assumed to be local in time. You see, it's just a derivative. It's just velocity at the very same moment of time which we consider, right? Is it clear? That derivative is taken at the same moment of time with everything else. So it's in a sense local in time situation. It doesn't have to be. What it means then is that your dissipation, in fact, general dynamics, but dissipation in particular can depend on the history, can depend on what happened to the system before we start observing it, right? And such system exists, and they become much more complicated than this simple equation, because that equation, because of locality in time, it's differential equation. if you have to take into account the whole history which happened before, it means that you need sum over all that little increments in time, and that means that the differential equation becomes an integral equation. And integral equations are much harder to solve than differential ones. And in fact, this is a big part of my research, which I'm doing right now, is exactly that thing. But you can think about it on the following way. What does it mean, locality in time? It means that you have an oscillator, right? And you have a bath, which oscillator is coupled to. And the oscillator, when it's moving, it disturbs the bath, disturbs the environment, right? And environment, what that locality in time means, that environment completely forgets everything. So you disturb it a little bit, that waves, that energy got transferred to the infinity, but the environment didn't change that much at all. It's way too huge, so it cannot change. But you can imagine another situation when an oscillator is going like this, and every time it leaves behind it some sort of disturbance, which is then propagates slowly in time. So next time when oscillator comes back, it actually feels that disturbance which was produced in the previous time, right? And then your dissipation will depend on the whole history. And it will decay with time, but will be decaying slowly, and then it becomes an integral equation, and everything becomes much more complicated because that depends on pretty much everything. Then and we still don't really know how to handle such situations. Well, we know how to solve equations, but what does it mean, and especially in quantum case, is still a mystery and still something which we are working on. So, but for what I'm going to talk about right now, this is not important. The fact that it's local in time is really not important. What is important is the dissipation is always decreasing the energy. All right. So, if it always decreases the energy, then and especially the kinetic energy, the dissipation decreasing energy, so it wants velocity to be zero, right? So you move in this particle, it has air resistance, and that particle wants to not to move. So then let's imagine that we have a system with some sort of potential energy. So there is a potential energy function, and I still consider only one-dimensional case because it's easier to draw, and it's actually easier to understand. There are some peculiarities which come in multi-dimensional case, but let's draw them. And so there is some potential energy, right? And let's imagine that we started our system with some large energy, right? So the total energy, the total mechanical energy, kinetic plus potential energy, will be decreasing because of the dissipation. The energy is not conserved. We have dissipative system. So the energy will decrease, right? So it means that this line of energy, which we always draw, will go down, and eventually it comes here, right? And at this point, the total energy equals the potential energy. It means the kinetic energy is zero, the velocity is zero, and the particle can stay at this point, or your system can stay at this point forever, right? Right?
Yes. Well, then why doesn't it?
Say it again?
Well, then why doesn't it?
I'm sorry, I still didn't hear you. Okay.
Why doesn't it?
Yeah, right. It will not, of course, because there is noise in the system. Noise means that there is some force on the right-hand side. There's always jiggling this system. So as soon as it comes here, it jiggles a little bit. And as soon as it goes a little bit down, it keeps going down. Right? So that means that noise is very important in the sense that it kicks the system out of wrong equilibrium. It cannot kick it out of the minimum, right? Because in the minimum, that noise kicks the system a little bit to the side, but it always returns back. Here it's not, right? When you kick the system a little bit out, it actually goes down. You can try to take something like this, right, and try to balance it on the tip, right? Well, presumably you can do that because it's a maximum of the energy, so it can stay here forever. But it cannot, because there is always noise in the system, and it will always kick it, and kick it a little bit, and it will fall down, right? So that's exactly what happens with any other system. It's so that noise is very important for the system to get to the minimum of its potential energy always. And there is one more thing about it, that it turns out that dissipation and noise are not completely decoupled things. In a thermal system, for example, when you have temperature, there is what is called the fluctuation dissipation theorem, and it actually tells you that if you have dissipation, you must have noise. There is no way around it, and it's a theorem. I mean, you really cannot do anything else about it. And the reason for that is, again, very simple. So let's imagine that we have a dissipation. It means that there is a coupling to a large system. Like, for example, that oscillator is coupled to air, right? When it's moving air around itself. But air consists of molecules, right? And those molecules hit that oscillator all the time, randomly. This is exactly the random noise. And we cannot get rid of it without getting rid of dissipation. So it's always the same thing in a thermal system. So it's what it means is that if you have dissipation, we always have noise in the system, and together those two pieces, those two effects, lead to the fact that the system will always go to the lowest possible energy. Now, if you look here, there are two minima here, and this minimum is at a little bit larger energy than this one. The system can get into this minimum. It's a random process, right? So it goes somewhere, and it eventually can get here, and stays there for a very long time. But if you have a noise, and it's statistical noise, then at some time, that kick, which is random kick right here, that force is random, that random force will be large enough to kick it out of this equilibrium, out of this wrong minimum to the correct one. And that system will still find it. So now, but this picture actually implies that it really doesn't matter how large dissipation and the noise are. They can be infinitesimally small. So we have almost pristine, clean system, but with just infinitesimally small noise and dissipation. And that still will, those two, noise and dissipation, will still lead to the system going down to the lowest possible energy, right? What depends on the strength of dissipation and noise is how long it will take for the system to find that minimum. If the dissipation and noise are very, very weak, then it will take very long time for the system to find its true equilibrium, true minimum. But if we wait long enough, we'll get there, right? Does that make sense?
Yeah.
So what it means is that when we have a clean system, so if you have any system, and we know that dissipation and noise are sort of small there, then we can assume right away from the beginning that the system is at the minimum of energy, right?
Yeah.
But then if we do some experiment, and remember, experiment means that we apply some force to the system with some frequency and see how it responds to us. Right? That's always experiment. We apply some disturbance and perturbation to the system and see how it responds. That means that the response of the system will be the response of the system around this minimum. Right? And if our disturbance is not large, of course we can kick, I don't know, our oscillator so hard that we actually break it. All right, then it will find some other equilibrium somewhere far away. But but then it is not a perturbation; it's a big thing. But if you just trying to figure out what the system is by itself, not what we do to it, but we want to know the properties of the system, then we disturb it as little as possible to get the response, and then figure out something about the response. In particular, what is the resonance frequency of the system? So the system now in the minimum, we disturb it a little bit, and it starts to oscillate. But close to any minima, so if this minimum is x naught, close to any minima, my potential energy must look like some constant, this constant, right? Plus some coefficient over 2 times x minus x naught squared. if there is no singularity in this function, which you pretty much always can assume that there is none. So, but then it means that it's an oscillator. That's an equilibrium length of an oscillator, and that's potential energy of an oscillator. And then your resonance frequency is given by the potential by the simple resonance frequency. And this is your spring strength. And all you need to do now is to find what is kinetic energy of your system. That can be complicated because it's not necessarily oscillator, but it will still be proportional to velocity squared. And then what you will have is just the standard oscillator. And you can now study, and you can now figure out what is resonance frequency by just from our standard formula, right? Or you can measure the oscillating frequency, right? It's a response function, so you can measure actually, and then from that response function you will know this number, so you will know the property of your potential energy close to the minimum. And that's how typical experiments are done, and how we know something about the systems. We measure their response, we look at the different resonances there, and see that each resonance corresponds to some sort of a minimum of potential energy. So we know some properties around those minimums, and starting from there, we can find out what is the width of that peak, what is the dissipation in our system around this minimum, and so forth, and try to figure out where it comes from, what it couples to, and what kind of experiments we can do to actually check all of our assumptions. And then, of course, the next step is what we can do to make something useful out of it, right? I mean, after all, we really want to do something useful with our knowledge, but not necessarily. It's okay if it's not useful, because who knows what can be useful next. All right? Does it make sense?
Yeah.
So that's why, remember, I told you that the oscillator is pretty much always a good approximation to your system. That's exactly the reason, because there is dissipation in noise in any real system, and it will always bring down the energy, and the system will always find the minimum. Now, there are some exceptions to that rule. I'm not going to go there in any depth, but one of the exceptions is what is called glasses. And a typical example is exactly a glass in your window. And the problem there is that the potential energy, if you think about the configurational space of all the molecules of glass, I actually don't know what they are. But if you think about the configuration energy, it has a lot of minimum, very deep minimum, and many of them actually. In fact, it's exponentially many. It's growing with the size of the system. And what it means is that it takes very, very, very long time for the system to find that minimum, to find the true minimum. It has to travel between minima, and the rate how it jumps from one to another. It jumps because of the noise, right? And the noise must be hard enough in order to transfer it from one minimum to another. And such noises, such big kicks, do not come very often. So it means that you have to wait very long time and for the system to find its true equilibrium. And in fact, in glasses, exactly such system when it actually never happens. So the glass which is in your window, it's not an equilibrium. It's actually flowing very, very slowly. But in 1,000 of years, if your houses are still intact and your windows are still not broken, then what will happen is that glass will become a puddle on the ground. It will actually flow down and becomes a puddle of glass. Because glass is not really solid. It's what is called glass. And there are some other examples like that. And one of them, some of them are magnetic systems which you never find its true equilibrium. And the other, I know, ice, for example, the normal ice made of water, is also very, very complicated material, and so forth. So there is a special branch of physics which deal with those. It's a glass physics. It's a very complicated story, and there are lots of computational power which is needed there, and it's very closely related to the NP-hard problems. If you have heard of those in computer science, and so forth. So it's one of the hardest problems in physics that we have. But in general case, I mean, except if you get rid of those exceptions, which you have to figure out what if you have an exception or not. But in general, it's a good assumption when you just approach a system. It's a good assumption. It is already in the true equilibrium, and we can use it to actually study it and to predict something and measure, and then from measurements know something about the function and so forth. We continue our discussion. All right, does it make sense?
Yeah.
Now, any questions? Sorry. Any questions? All right. Okay.
Makes sense so far.
All right. So I just again I want to point out a very very interesting story here that it really doesn't matter how small dissipation and noise are, they still play a huge role. It just takes them a long time to do that, but they still are major things which we assume, right? We always assume that the system in equilibrium, and that's because we know that those things are there. We may not know what they are and how exactly they work, but we know that they typically are small, not necessarily, but typically are small, and it really doesn't matter how small they are, they still bring the system down to the energy. And I should say that I'm always talking about one-dimensional oscillator, but it's only to save time and to save some pain in mathematics. We can also do the same thing in multi-dimensional system with many coordinates, and it's exactly the same story. But mathematics is more complicated, and but that story is applicable to pretty much everything. If you have a table right next to you, right, or desk, whatever, it's in equilibrium, right? If you try to disturb it, you knock on it, right? Then you hear a sound which is coming from that when you knock on it. You can try. And that experiment, right? It's a very profound experiment. And what it means is that when you disturb it a little bit, it's an equilibrium. You disturb it a little bit, you have that oscillating waves propagating on the surface of the table, and that's exactly the same thing. It's pretty much an oscillator which just oscillates. I mean, it's a bunch of coupled oscillators, and then they produce waves together. But it's basically the same physics, as I said. It's just mathematics is different, and we'll talk about waves a little later. And then it is described by pretty much the same story. It's a bunch of oscillators, each of them they couple, but each of them is pretty much the same, and you can do almost the same math which you have done before, but you have to include some linear algebra on top of it, and to find all the frequencies, all the sound frequencies, and so forth, and we can find how sound propagates, and so forth. So what I'm saying is, it's not just an oscillator. I'm talking about an oscillator, but you have to understand that I just cannot go any further than that, but it works exactly the same way for pretty much any material you want. Right. So the same thing is with when you shine light. It's the atoms are in equilibrium, so light is coming and disturbs it a little bit. Electrons and atoms starts to oscillate around their minimum position. When charged particle is oscillating, it shines light back, and that's what you see. It's exactly what's called reflection, and so forth. So it's all there. It's exactly the same story. But it also tells you what is a general procedure is. So imagine that we have that potential function. Then what do we, and we want to describe a real system in that potential function. So what do we need to do? Well, we need to find all the minima of the potential. This is u, right? Okay. We need to find all the minima of the potential. Just taking the derivative of du over dx, find where it's zero, right? Find all those minima, and you will find also the maxima, right? You will find all those extremum points by doing this, by solving the equation du over dx equals zero, right? You solve this equation, you find at which axis, at which coordinates it is zero. You find all the minima, all the maxima. Then you compute the value of the function u at each minima or maxima. You find the place where it is minimum. The minimal out of the finite number of points. You can always do that. It's finite number of points. And then around this minima, you take this minima. Around this minima, you take your function u, and you use a Taylor expansion about this this minimum. Right? The Taylor expansion is telling you that u, when x is close to x naught, equals to u of x naught, which is just a constant. You remember that there is a potential energy, you can get rid of constant all the time. Then it must be du over dx calculated at x naught times x minus x naught. That's the next term in Taylor expansion. And the next term in Taylor expansion will be 1/2, then second derivative of u over dx squared at x naught times x minus x naught squared. Right? That's a Taylor expansion, simple Taylor expansion. But now what you see here, that x naught, remember, it's a solution of this equation. So it's exactly the point where this derivative is 0. So you get rid of that. And what you find is that this k is nothing but du, second derivative of du over dx at point x equals x naught. Right? So your standard procedure then, if you know the function u of x and you ask what are the small oscillations about the minimum, you find the minimum. Right? At that minimum, you use Taylor expansion, or just simply calculate this the second derivative at the same point, and you find and this is your k, right? Then you find your kinetic energy at the same at this point, and what you get is then simple k divided by m squared, what is your frequency. Right? Does it make sense?
I had a quick question.
Yeah, sure.
So the resolution for my screen is low. I think it's my bandwidth. I just wanted to ask if that's on the lecture notes.
Well, somewhat yes. I mean, I will use that procedure later on, and it is in the lecture notes how I use it. Here I just describe it, what I'm
okay
later.
Okay, thank you.
Sorry about your resolution. I don't know what to do about it. Maybe you should push the university to provide you with better internet. And come on, you're paying tuition and fees. Those fees supposed to support services in the campus, but you are not in the campus. Sure.
Oh, I know.
You can write some sort of, like make a campaign to demand that the university pays for some of your internet. I would support it. All right. So that's the general procedure, and that's what I'm going to use later on. But before I go there, and before I describe the problem which I want to consider, I want to return very, very much back, one of the first lectures. And when we derived that f equals ma, well, we didn't derive it. We sort of argued that it's plausible to have such a law, and then we just say that okay, we will take it and we make predictions and we measure and then see if they coincide and if they support our hypothesis. And they do everything. I mean, it works wonderfully. So f equals ma, and one of the things which I was telling there is that we want all our laws of physics to be translationally invariant. It means very simple things, that if I write laws of physics in this point of space and I write them in this point of space, then all the equations will be the same. F equals ma here, F equals ma here, right? You can assume that it's not necessarily so. You can even say that our space is completely different in different points, so it is f equals ma here, but it is f equals ma cubed over here. And then we are in trouble, right? Because then we need to know a lot more in order about our space in order to make any sort of predictions. And we would probably not be able to do that. But it turns out that it works quite well. We assume that, and it works quite well. And in every point of space, the laws of physics are the same. And you can say that it's just simple mechanics, but it's the same principle actually works for everything. We do it exactly the same way for quantum field theory, for theory of relativity, for everything. Because again, if it is not so, we have very hard time understanding what to do. How do we describe space which is inherently not translation invariant, not uniform? So we assume that it's uniform and we use it all the time. But if you think about it, then it's kind of it's kind of weird, right? So the laws of physics are the same at this point and in this point. Everything is the same. If I want to calculate anything, it's the same thing, whether I'm here or here, or go to the next room, or even to Houston, right? And it's all the same laws of physics. So the laws of physics, the laws which governs everything, are translational invariant, right?
Yeah.
Right? Okay. You're never worried about whether you need to write F equals ma if you're in California or in Texas, right? It's still the same thing.
Right.
Yes.
That's exactly what I'm talking about. That means that F equals ma, it's translation invariant laws. But our world is not translation invariant. You see, I can walk around here, right? But I cannot walk through this wall. I tried. Didn't work. Right? So, but the laws of physics here and the laws of physics inside this wall must be the same. The laws of physics are translation invariant. There is no way to say that F equals ma inside my room, but inside that wall F does not equal ma. No, it's still F equals ma there, even inside this wall. All right. So how come laws of physics are all completely translation invariant, but our world is not? Why?
Because we've chosen the laws such that they are translation invariant. We invented the definitions for the laws, right?
Yeah, and they work. And that work is translation, and they work if we assume that they're translation invariant. But and they're supposed to describe all that world around us, right? But the world is not translation invariant. But the laws do work. We know them. We check them. So it looks like this is the simplest possible check which you can do, and it sort of contradicts our fundamental laws of physics. The world is not translation invariant. Right? So at this point, you can think that all that F equals ma and everything else is completely BS and should be thrown out, and we need to start anew and then try to figure out what to do with the world which is not translation invariant. And it becomes very hard. So you can as well just give up and go sell fries in McDonald's. Oh, I should do it. And but it turns out that it is actually not correct. The story is that the laws of physics, the fundamental laws, are translational invariant, but the world which is around us is not, and this is no contradiction here. And because you have to understand that very simple distinction between those two facts which I'm talking about. The laws of physics are equations of motion, the equations of what governs our systems. What we do observe around us is the solutions of those equations. Okay? You see the difference? There are equations and there are solutions of those equations. And what it turns out that solutions do not have to have the same symmetry as the equations. Equations can be completely translational invariant, but the solutions will not. Right? And that is called spontaneous symmetry breaking, because it's not something which we do to a system. It's what system does on its own. And one other example, which is sort of more in line with what I'm talking, because here with the wall, you can say that there's a construction people who came here and then put it there. And that's, of course, correct. But so I give another example of it. You all know the magnets, right? Those things you put on the refrigerator. So if you take a magnet and you heat it up, right, it will lose that magnetization after some temperature. That's a phase. There is a phase transition when ferromagnet or magnetic material becomes non-magnetic at high enough temperature. Before it melts, it becomes not magnetic. Now, let's imagine that we start with that state, which is not magnetic, and we lower temperature. So we don't do anything to our system, right? We don't like, take the magnetization and put it in some particular direction. No, we just lower the temperature. The temperature is a scalar, it has no vector quantity, so we do not choose any kind of specific direction for our magnet. And we lower it, and eventually magnetization appears. Now, magnetization, as you remember, is a vector, right? So it means that it's not only appears, it's not only magnitude is not zero, but it also picks some sort of direction at which it will appear. But all the directions are the same. Well, it's not necessarily so in a crystal, but we can assume even in a crystal that there is no difference between different directions. It can be done. It takes a little bit more work, but it can be done. So it means that then our magnetization picks our global magnetization of our huge magnet picks one particular direction at which to point, right? Everywhere.
Yeah.
But if all the directions are the same, and actually the equations which govern those things are they have that symmetry. If the rotational symmetry, all the laws are completely isotropic, and so then the magnetization picks some sort of direction, and which one? How does it know which direction to pick? Do you know?
I do not.
Probably not, because it was one of the mysteries of the physics of the last century, which eventually was solved by the guy whose name Lev Landau, one of the greatest physicists of ever lived. And he's done a lot of work, but that one is called, what I'm talking about is called spontaneous symmetry breaking and the Landau theory of phase transitions, two names which are sort of the same. And so what actually happens there is that at some point in the temperature, that magnetization must appear. Now, which direction it will pick is completely random. There is no way to predict it. We can predict that it will pick some direction, but we cannot predict which one, because it depends actually on noise on the system. And noise we call it noise because we cannot predict anything about it. But we do know that it will pick, nevertheless, will pick some direction. Right? So, but as soon as it picks the direction, the isotropic, the symmetry with respect to rotation is broken. Right? This is the state when all magnetization point in this direction, and the state when all magnetization point in this direction are different states. Right? I have to describe my magnetization. Here or there. So those are different states. So although my Hamiltonian or my theory of those magnetic systems are completely isotropic, the state which appears as a solution of those equations is not isotropic. So the state actually has lower symmetry than the theory itself. And that is exactly why is it called spontaneous symmetry breaking. I'm lowering the temperature, and all of a sudden, spontaneously, the system picks one particular direction. Why it's picking this direction, not this one, depends on noise, which it means that I cannot predict it. But I can predict that it will pick some particular direction. Okay, and that's exactly what happens with everything else. And it's actually quite a profound idea. It turns out it describes a lot of different physics. All that magnetization physics is described by that theory. It's also, if you heard about superconductivity, when you have a current which can go in a loop forever and never decays, it's a superconductivity. It's also in that described by the similar theory. It's superfluidity. I've already talked about it. That if you have a pipe and you put liquid helium inside and set it in motion, it will go around that loop forever and never will decay. It's also described by the very same ideas. And if you ever heard about Higgs boson, which was discovered in LHC a few years ago, and was predicted a long time ago by Higgs. That's why it's called Higgs boson. And it's also the same thing, and it's for our understanding of fundamental structure of all the series, of all the universe. That's extremely important thing, because it turns out that we cannot otherwise understand why some of the particles, elementary particles, have mass. In the theory itself, we have to assume that they're massless, otherwise we cannot write a theory. That's it's kind of strange idea, but nevertheless it is so. But in experiments they do have mass. So it was for a long time people did not understand where does the mass come from, and it turns out that there is another field which cannot be observed because it's everywhere, and it can be observed, but it requires a lot of energy. And but in normal experiments it cannot be observed, and it has undergone some phase transition already because our universe has cooled down. So at some point it condensed and it picked some sort of direction not in the real space, it's some other space. And and that's exactly what gave the masses to the elementary particles. It's called now Higgs mechanism, and it's an essential part of what we know about how those system works, how our theories work. And so, and it's very important. That theory is very important as a tool to predict what's going on to system like magnets, like liquids, whatever. And it's also a very important tool to understand the fundamentals of fundamental properties of our universe. And so what I'm going to do now is I'm going to actually show a simple example of the very same process on a simple mechanical system. It is not exactly, I mean, I have another mechanical system, and I will show it tomorrow, well, not tomorrow, next lecture, if I don't forget to bring it. And it's which illustrates that idea, well, how it happens that the symmetry of solution is different than the symmetry of the equations. But that example, that other example, which I will show next lecture, is actually very, very close to real theory of phase transition. But unfortunately, it's mathematically more complicated to do. And it's possible, and if you take my class in analytical mechanics, I actually do that there. So I will show it on some other example, which has all the features of the phase transition, and which is much more complicated. Sorry, much simpler than anything I can think. I specifically tried to find something very, very simple which would illustrate those ideas. So that's what I'm going to do today. And so what I'm going to do, I'm going to consider a very simple mechanical system which illustrates the idea of symmetry breaking and tells you that it's actually possible to do. So let me do that. So first I'll describe the system itself. It's very simple. Something which you can do on your own if you want. So let's imagine that we have a hoop of radius r. Okay, and now that hoop is staying in vertical plane. So I keep it here, like here's my hoop, right? And now I start to rotate it with respect to the diameter vertical. It's vertical. Okay, better. With the frequency, with the angular velocity omega. Okay, so that's a hoop which is rotating with the angular velocity omega. All right, and on that hoop there is a little bead which can actually slide around that hoop with no friction. And I said no friction. It means that friction is very, very, very small. I can neglect it when I solve the equations, but when I try to find the equilibrium position, I will have to assume that my energy is the lowest. All right, and that little bead has mass m, and it can just move around. Is it clear, the picture?
Yes. Are we assuming that the hoop is not?
Sorry, you were interrupted. Can you repeat?
Are we assuming that the hoop is massless as well?
Well, its mass will not matter. I'm rotating it with a fixed velocity. It's not like I twisted it and let it go. That will be completely different question, different problem. Actually, a little bit more complicated. And what I do, I just attach a motor here to the hoop, and I'm rotating it with a constant velocity. No matter where the bit is, the velocity is always the same. And this situation, the mass of the hoop doesn't matter because it's not a dynamics. Its motion is given. I already know that it's just rotating. That's it. I don't need to solve equation for its motion.
Okay, thank you.
Okay. So, but it's a good question because the other problem is would be that I twisted it and let it go. Then, of course, when that bit goes up here, if it goes up here, then the frequency of rotation will slow down, right? And how much it will slow down depends on the mass of the hoop. And then I need to solve two equations for the motion. I need to solve the equation of motion for the bit and equation of motion for the hoop itself. I don't want to do that. I want to solve simpler problem. I just fix that frequency of rotation, then velocity of rotation. And then I don't need to know anything else about that hoop. It's just rotating with fixed velocity. Okay? That makes sense?
Yeah. Yes.
All right. So, what do you think will happen to the bit if I do that?
Well, it's going to move up the side of the. It's going to move up the side of the hoop.
But if my velocity is 0, it will not, right?
Yeah.
So, then your answer is not universal.
Well, we'll move up the side of the hoop as a function of the velocity then.
All right, that's good. Anything else? Any other ideas? Come on, guys.
And on the initial position of the bead.
Okay, it's exactly at the bottom. That's a good question. You must have initial conditions. So initially it just stays there. It has 0 velocity and it just stays there. But will it go up at all? No.
Well, it won't decide whether it goes left or right because that depends on the way it's rotating.
Okay, but you actually said something about that velocity. What was that? Assuming that. Right. So what does it mean?
The faster you spin it, the
higher.
higher.
Yeah, I understand what velocity means. I don't understand what high enough means.
Well, that means it has to overcome something to rise, right?
Yes.
I don't know what it's overcoming, though.
Good, very good. It's gravity, right? It has to. There's gravity here. It's vertical.
Right. That would make sense.
So yes, that's actually correct. And so there is some critical velocity, critical omega c. C is critical, right? Such that if omega is less than omega critical, then the bit will actually stay down and not move. It will not move. Now, if omega becomes larger than omega critical, then the bit starts to move either to the right or to the left, right? And whether it moves to the right or to the left is determined by the noise, because the system is absolutely symmetric with respect to left to right. There is no difference between going to left and going to the right. I mean, it's rotating, so you need to understand that left to right means. Let me color that part of the loop red or that part of the loop green, right? And then I ask if whether it's moved to the red or to the green portion of the hoop. And whether it goes to the green or to the red is completely arbitrary. It's only determined by noises. in the system. Whatever is a little shift here happens to whatever side, it will go there. But it will go there, right? And we can compute how much it will go up, but we cannot compute where. Now notice that system again. The system is completely symmetric. This side, red side, and green side of it are completely the same. There is no difference between them. I mean, it may not be visible in my picture, but let me imagine that it's a perfect circle. And but the system chooses only one place, either to the red or to the green. So it breaks that symmetry between red and green portions, right? So that's exactly what I was trying to describe. That all the laws, and I will show it explicitly, are completely invariant and the changing. So it's red to green or left to right. But the state which appears is not symmetric. It's either on one side or the other. It cannot be on both simultaneously.
So I'm not sure I understand that, because the thing is rotating in a certain direction, right? Shouldn't the direction of that rotation control which side the bead decides to go up on?
Very good. Very good. It's a very good question, in fact. But think about it. Rotation is just a vector, right? Omega is a vector. I mean, it's rotating around one particular axis. So how can you, knowing only the direction of one vector, find out some direction in the plane which is perpendicular to it? What kind of construction can you make to do that?
I'm sure there is one. I don't know, though.
No, there is none. It's impossible. You need two specific directions to do that, and there is only one. Omega and G are on the same direction, on the same line. There is no difference between different directions in the plane which is perpendicular to them. So no, it's actually completely irrelevant what direction of omega is. You can go clockwise or counterclockwise. It will be exactly the same. There is no difference between those. All right, and you will see that from the equations. It's actually easier to see there. All right. So, but that's the results which we want to consider. Now, if you think now about it, that when we're rotating it, when omega is less than omega critical, the bead stays here, right, at the bottom. And now, if you come around and push it a little bit, it will start to oscillate around the minimum, right, around the bottom. And those oscillations will have some frequency of oscillations, and that can be computed by the general procedure which I described before, and we will do that. And also when omega is larger than omega critical, the bead will be staying here at some particular angle. But then if we come around and poke it a little bit, it will start to oscillate around this particular angle. And again, those frequency of oscillations also can be computed. And moreover, they actually can be measured. If you think about it in a sense that, let's imagine that this is our molecule, and that molecule is rotating somehow. I mean, it's never so, but you can let's use our imagination. So this is just some charged particle, very small, so we can actually not see what's going on there, but we can shine light on it, and if if this particle is charged, when we shine light on it, we will, if the frequency of the light is in resonance with the frequency of those little oscillations, then we will have additional absorption in our light, of our light. And by using that, exactly that response which we studied last lecture, we can actually figure out what those frequency of oscillations are. And using that, we can actually find out how fast that hoop is rotating. Okay. So that's one of the reasons why it's so important to know the response of the simple oscillators. We can actually measure something which we cannot see by measuring the properties. All right, so let's then start just doing that. Let's just start this problem. And now That problem can be solved in many different ways. You can use Newtonian mechanics, Hamiltonian mechanics, whatever you can formulation. But I will use Lagrangian because I like it better. And so I need to, in order to find Lagrangian, I need to find kinetic and potential energy. The position of my loop, my bead, is can be described by just one angle, theta. That angle from the minimum. So this is the only number which is that number completely describes the system, because I know that how hoop is rotating. It rotates with the frequency omega. So I always know where this bead is along this circle, right? And the only thing which I don't know is where it is along that hoop. So that is the only number which is my coordinate. And Lagrangian can be written in any coordinates. So this is my coordinate. And now I need to write potential energy. Well, potential energy I know how to write. It's just how high it is on top of that of the minimum. So the potential energy which I have is just mgr 1 minus cosine theta. It's the same as for the pendulum. Right? Does that make sense? Yeah, I don't need to think much about it to write those things. And now I need to write the kinetic energy of my system. That kinetic energy consists of two parts, simply because there are two velocities. When my theta is changing, remember the potential energy, kinetic energy is when coordinate is changing. When theta is changing, my bead is moving up and down, right? So velocity at which it's moving up and down, is r times theta dot, the same as in pendulum. So that's velocity along this direction, but it also has velocity along the direction which is perpendicular to the blackboard, right? Because the hoop is rotating. So this point is also moving. Well, if it's rotating this way, this point is also moving inside the blackboard, right?
Yes.
So, and that velocity which is inside the blackboard is given by frequency of rotation times this radius. This radius is r times sine theta. This is velocity which goes inside the blackboard. Okay? Now, think about it. This velocity is inside the blackboard, right? It's here. This velocity is perpendicular to the blackboard. So this velocity and this velocity are perpendicular to each other. Right? One of them is going this way, one of them is going this way, and the other is going this way. They're always perpendicular to each other, no matter what. Right?
Yeah.
But then by Pythagorean theorem, right? The square kinetic energy is the square of the velocity, right? So I need to put m over 2, and here I need to square of the total velocity. But the square of the total velocity, when I have two components which are perpendicular to each other, is the sum of the squares. So I have r squared theta dot squared plus omega squared r squared sine theta squared. That makes sense? This is one component of velocity, this is another component of velocity, and they perpendicular to each other. So the square of the total velocity is just the square of the sum of the two velocities. No, the sum of the squares of the two velocities, sorry. Does that make sense?
Yeah.
So this is my kinetic energy, this is my potential energy. So my Lagrangian then is kinetic energy. This is my Lagrangian. Kinetic energy minus potential energy. Minus mgr 1 minus cosine theta. Okay? So let me open those brackets and write it this way. mr squared theta dot squared. Oh, let me write it better. mr squared over 2. And here I have plus, and what was it? M over 2. That makes sense? Now, if I know the Lagrangian, I can write the equations of motion, right? It's the Euler-Lagrange equation, which we studied before. It's d over dt. dl over d theta dot must be equal to dl over d theta. Right? Now, before I do that, and that's it, that's enough. I just make this function differentiated, that's it. I got the equation of motion. No problem with it. But I want to use some trick here, because it is simple to use here. So what I want to do is to say that now notice that after that step, after I wrote the Lagrangian, right? I do not need to worry about what is the kinetic energy and what is the potential energy. In order to write equations of motion, I only need the Lagrangian itself. Whatever part of it I call kinetic energy and whatever part I call potential energy has no bearing on anything. They're all the same thing. I mean, they all come into the equation, right?
Yeah.
But then it means that I can relabel the terms of my Lagrangian the way I want. And the way I want them to relabel is the following way. I say that my kinetic energy is a part which depends on theta dot. And that's the kinetic energy. And then whatever is here, which does not have theta dot inside, you see that it depends only on theta, I will call potential energy. Right? So what I have then is my effective potential energy. Let me write it here. My U effective equals whatever is there is minus m over 2 r squared omega squared times sine squared theta plus mgr 1 minus cosine theta. This is my effective potential energy. And then, if I use that, my Lagrangian looks like this. Minus U effective of theta. Right? That makes sense?
Yeah.
All right. But look at this. If I change instead of theta, I will use the number x, the letter x. That will be just your standard kinetic energy, mv squared over 2. Well, r squared is going inside m and forget about it. It's just another matter. And here I have potential energy which depends only on theta. Right? And then I actually know what the equations of motion are. This is just a single particle with which coordinate theta moving inside in this potential energy. So my equation of motion then is just mr squared. This plays the role of the math. Theta double dot equals minus du effective over d theta, which is of course exactly the same on this one. Right? That makes sense?
Yeah.
All right. But then, what I do, I will just do the same analysis as I've done all the time for just a particle, normal particle with mv squared over 2, right? One-dimensional particle, which is moving in the potential field. So what I do, I just draw this function. U effective as function of theta, right? And find some minimum and maximum for it. I'll do it a little later, but here again, I see that in order for the beat to be in equilibrium, right, when it's staying put at some point, and it doesn't matter where it is, this must be 0, right? So acceleration must be 0, otherwise it doesn't stay put, it just starts to accelerate. So it means that U effective derivative of U with respect to theta must be equal to 0. But that's exactly the definition of the is a minimum of maximum of my potential energy. So all I need to do is just to take the derivative of this function and write down what is and solve when at which theta it equals the derivative equals to 0. Right? That makes sense?
Yes.
This way you can look at it either way, just to say that at theta, which is where this derivative equals 0, this also must equal to 0. The acceleration must also equal to 0, and then it means that if I put my bead exactly at that angle, where is it that effective where the derivative equals 0, it will stay there without for forever. Right? That's one way of saying it, and the other way of saying it is that this is a minimum of that's the condition for is a minimum of maximum of my potential energy, and we know that those are equilibrium points. Those are the same thing. That's saying the same thing, just from different perspectives. So all I need to do now is to take the derivative of this function. Well, I can do that, and so I have minus here, so I have du over d theta effective over d theta equals, now it is minus m r squared omega squared, and then I have sine theta cosine theta. That's the first term, and the second term will be plus. Here this is minus. Here is plus because it's minus cosine. It's sine, so it's m gr times sine theta. Okay, does that make sense?
Yes.
And now, in order to find the position of the equilibrium, I need to find such theta naught, where this is 0. Okay? Does that make sense?
Yeah.
So I need to solve this equation. And let me do that by the following trick again. I take the sine theta to outside of the brackets. So here's, let me write it. The cosine theta plus mgr times, and everything is times theta naught equals 0. Okay? Does make sense so far?
Yeah.
Yeah.
So we need to solve this equation, right? Now this equation is 0, right? And if we have two factors here, and in order for such expression to be 0, at least one of the factors must be 0. So this then the solution, this equation, it actually means that either theta naught equals sine theta naught equals 0, or cosine theta naught equals let me write it, mgr divided by mr squared omega squared. So I can cancel m here, and I can cancel r here, and I have g divided by r omega squared. G divided by r omega squared. Okay? So it's either this condition or this one. Then it is 0. Does it make sense?
Yes.
Yeah.
Yeah.
All right, good. Now, every time, just please, every time you're solving a problem and you get something like that, the first thing which you do is to check units. All right, so sine of theta naught is dimensionless number. So it means on the left hand side is dimensionless number, so on the right hand side it must be dimensionless number. The dimensions for g is meter divided by second squared, or length divided by time squared, right? R is length, and omega is 1 over time. So r times omega squared is length divided by time squared, right? That makes sense?
Yeah.
Just checking units. So what you have here is length divided by time squared here, and here is length divided by time squared here. When you divide them, you get dimensionless number. So that expression has a chance to be correct. It doesn't mean that it's correct, but it has a chance. If the units do not coincide, that's it. You made a mistake. There is no way to have a formula where the units on the left-hand side are not the same as the units on the right-hand side. Such situations do not exist. That's what math is all about, basically. All right, so here's the units I checked. Now, the next thing, we need to analyze those equations. So let me say the following. Let me now draw the circle. Right? And see what those equations tell me. The sine of theta not equals 0 corresponds to theta not equals 0. This is one solution, right? And it also there's another solution here that theta not equals pi, and that means this point, right? That makes sense?
Yes.
So those 2 points are some sort of extremum of our function, some sort of equilibrium, is a stable or unstable. And looking at that, you can say that this is unstable, this is stable, but that's not exactly correct. Only half of it correct. Now let me look at the other equation, this one. And that's a more interesting equation, because it depends on omega. Oh, by the way, notice that everything depends only on omega squared. Right? Do you see this? There is only omega squared in the potential function, and there is no linear in omega terms. Right?
Yeah.
But it means that the change in sign of omega doesn't change anything. So rotating in this direction and rotating in the opposite direction is the same thing. Okay? That makes sense?
Yes.
All right. So now let's look at this equation, and it depends on omega. Now let's imagine that omega is very small. That omega is very small. Then this number is very large. Right?
Right.
But cosine cannot be larger than 1. So if omega is small, this equation has no solution. The first solution appears when this expression becomes 1, equal to 1, right? So the first solution of this equation appears only when omega equals, let's call it omega critical, right? When omega equals omega critical, which is G divided by R squared. If omega is less than omega critical, there will be no solution of this equation, right? But if omega becomes larger than omega critical, then I have a solution. Now let me just rewrite this equation in terms of omega critical. What I have here then is omega critical squared divided by omega squared. Right? It's the same equation, just with that omega critical here. So what you have here again, if omega is less than omega critical, then this number is larger than 1, and there is no angle cosine of which larger than 1. No solution. If omega becomes larger than omega critical, right, another solutions appear. And because cosine is symmetric with respect to change theta to minus theta, it's actually 2 solutions which appear. One of them here, I don't know if you can you see it? Right, and the other is here. That makes sense?
Yes.
critical omega. Now, we need to know which one is the maximum, which one is the minimum here. So let's imagine that omega is less than omega critical. Then those two red solutions do not appear. They don't exist. But then we know that this is the maximum, right, of potential energy. This is the minimum. So the bead will stay down there, exactly at the bottom of my hoop. Right? But then, when omega becomes larger than omega critical, two new solutions appear. Now, it's kind of obvious that this still will be a maximum, right? Is it obvious? But you see that in one dimensions, minima and maximum must go one after another. If I have a minimum, the next will be maximum. If I have a maximum, the next will be minimum. You cannot have two maximum in a row. It doesn't make sense. All right? So it means that this, if those solution appears, this is a maximum, then this is a minimum. Then this is a maximum again. And this is again a minimum. So as soon as that omega becomes larger than omega critical, two new minima appears, and what was minimum before becomes a maximum. Right? That makes sense?
Yes.
So what it means also is that, but you see that everything is still symmetric with respect to left to right. Right? But now I have two new minima appearing. One to the right, one to the left, one to the red, one to the green. And my system will be in either this one or this one. So exactly around omega, close to omega critical, the symmetry gets broken of my system. All right. Now, let's look at how it actually happens. And in order to do that, I want to draw pictures, and I don't have any place for it. So I want to draw this function as a function of theta. Now notice when omega critical is omega just above omega critical, just a little bit above omega critical, right? Then this cosine is very close to that ratio is very close to 1. It means that cosine is very cosine is very close to 1. It means that theta is very small. So I need I need this function only for very small theta. So that's what I'm going to draw. I don't want to draw it for the full function, although you can. I mean, it's you have, I don't know, mathematically just plug it in and draw it. So let me see how it looks like. So this is my theta. Sorry. Yeah. This is my theta, and I only consider small thetas. And this is my u as function of u effective as function of theta. And I want to draw it here. And the first case, I draw it for omega smaller than omega critical. Sorry, omega smaller than omega critical. I have one maximum, and here for small angles, I just have minimum. So what I have is this kind of function, right? It's a minimum, right? So every minimum looks like a parabola close to it. Right, something like that. That makes sense?
Yes.
So this is for omega less than omega critical. But now I want to go to omega larger than omega critical, and I must have two new minima appearing. Right? So what will the only way to do that is to draw it like this. And this red line is for omega larger than omega critical. So you see that point, the bottom, theta equals is 0, becomes maximum, and here I have two new minima. And my bead will be either here or here.
So what about as omega gets larger, that it's greater than that maxima? Do we not care about that?
What do you mean? Omega can be as large as it can. everything stays the same, right? So when omega becomes very large, cosine must be very close to 0, right?
Okay.
And cosine is 0 when theta is almost pi over 2. It means that that might be this is a here or here, right? But that's what you would expect, right? It goes as far from the axis of rotation as it can. That makes sense?
Yes.
All right. So that's exactly the story of that symmetry breaking. So but now notice that all we need to do now is to consider a situation when omega is close to omega critical in order to consider that symmetry breaking case. That omega is close to omega critical and theta is much less than 1. It's very small. So theta is very small here, right? And omega is close to omega critical. So I want to consider exactly this situation. I want to say that what I have is my effective potential energy, and I want to take very small theta and very small and omega close to omega critical in this function. So when theta is very small, this gives me theta squared, right? That's sine squared. And that gives me theta squared, and I actually need the next term, theta to the 4th. Because I'm considering not the equilibrium position, I'm considering just 0. And it's either equilibrium or not equilibrium. I don't know that. Depends on omega. So then what I need to do then is to say that let me write it out. So all I need to do is to consider that omega for very, very small thetas, and I need it to the 4th order in theta. Again, this is a Taylor expansion. I'm not going to perform that. This is here. It's actually done in my lecture notes, and I'm already pressed this time. And the answer will be the same, the following: that E effective for very small theta is approximately equal to. Let me write just the final formula: r squared omega critical, and then omega critical minus omega theta squared, and plus 3 divided by 4 factorial, and I have here m r squared omega critical squared theta to the 4th. Okay. So this is that's how this function looks like for very, very small thetas. And omega critical is just this combination, nothing else. All right, that makes sense?
Yeah.
Well, you can think about it. Just take those sine and cosine, take the Taylor expansion of them for small thetas, plug the Taylor expansion here, and keep only terms which is up to the theta to the 4th order. That's all. There is nothing else. There are some other terms, but they're not important. I can prove it, but I will skip that part. So now you actually can see what happens. Why is that all of a sudden this line switches to this one? Consider very small theta. This thing. Right? What happened here when omega is smaller than omega critical? I have a parabola with the horns going up. And that's exactly this parabola. You see that when omega is less than omega critical, this is a positive number. And the horns go up. Right? But when omega becomes larger than omega critical, this becomes negative number. And it means that the horns of this parabola must go down. And that's exactly what it is here. Right? Does it make sense?
Yes.
Yeah.
Eventually, in either case, the horns must go up. Simply because for large theta, this term is most important one. theta to the fourth for largest theta is larger than the theta to square, theta squared. So eventually everything must go up. So here the horns of parabola go down, but eventually they must go up. So there must be two minimum. But also notice that it's absolutely universal situation. In any case, when you have this kind of potential energy up to the fourth order, right? If you have the coefficient in terms of the second order of your parameter, whatever the coordinate you're using, it can be magnetization, it can be, I don't know, superconducting order parameter. It's actually called order parameter in zero phase transitions. That's that coordinate which you consider. In any situation when you have the fourth order, right, which is and this is always positive. That part is and then you have squared that parameter squared and the coefficient in front of it changes sign. Then you must have the situation exactly the same as this one. So there must two new minima appear. And the system must choose either one or the other one. And then it will be a symmetry breaking situation. So this result is completely and absolutely universal. Okay? That makes sense?
Yeah.
So now we actually can with this function, it's much easier to work with than with this one. Right? It's just a polynomial. So let's forget about large. Let's say that our omega is always close to omega critical. By the way, in the serial phase transition, it is not omega here. It's not parameter. It's not omega. It's a temperature, but it has exactly the same structure. When temperature goes through the transition temperature, that coefficient changes sign. That's all. So again, there is nothing else you can write. It's the simplest possible. It's just the polynomial. Really the simplest possible case, and it's one of the most beautiful discovery in physics. That's such a simple story describes pretty much everything on the phase transition. So we can now do the. Remember that we can compute what is the oscillating frequencies in different minima. So in order to do that, we first again need to solve this equation, which we have already. That E effective divided by the first derivative equals 0, right? And that's exactly the solution. Right? And for small theta, you can write that cosine equals to 1 minus theta naught squared over 2, and that equals to omega critical squared minus omega critical if you want, and then solve for theta naught. Right? And that's what you will have. I probably don't have time to do that. So let's do that. We say that when omega very close to omega critical, those two minima they're very close to 0. So theta is still very small. When omega is just a little bit above omega critical. So what I have here, I can consider theta naught to be very small, and what I have is 1 minus theta naught squared over 2. This is the Taylor expansion of cosine. Must be equal to omega critical squared divided by omega squared. Right? So now I just write that theta naught squared equals 2, and here I have 1 minus omega critical divided by omega like this, and z squared. Right? All what I have is that theta naught. Let me write it somewhere here. I need to take the square root. So theta naught equals square root. Here I have 2, and here I have omega squared minus omega critical squared divided by omega squared, right? But now my omega is very close to omega critical. So if I write that standard tricks which we always use. So it's omega minus omega critical times omega plus omega critical, right? But when omega is close to omega critical, this is 2 omega critical, and this is just omega critical. So what you can write here is for omega critical. So the answer, and I've done it in my lecture note, the answer is just 4 omega minus omega critical divided by omega critical squared. So this is my theta naught. Right? So by knowing theta naught, I then can go in with either this or this potential, doesn't matter much, and compute the second derivative of that. Right? And then I will find what kind of parabolas are here. And from there I can find what is the frequency of the oscillations. Does that make sense?
Yes.
All right, I don't have time to do that because I want to show something else. But it is done in my lecture notes. For some reason I talk slower later. I used to be able to fit everything in one lecture. So let me then do the following graph. Let's imagine that I measure that theta naught as function of my omega. So this is my omega, and this is theta naught. Right? Then there is some critical, omega critical here. And when omega less than omega critical, all I have is just 0. Right? Theta naught equals 0. But then when omega becomes larger than omega critical, and notice, by the way, if omega is less than omega critical, I have square root of a negative number. So theta naught becomes imaginary, and those such angles do not exist. That's another way to do it. So if omega becomes larger than omega critical, what I have is square root of the difference, right? Right?
Yep.
Yeah.
So what I will have then is a square root here. The square root singularity. Okay? So that's a very typical situation again, how everything in the phase transition, theta naught then called order parameter, omega is typically the temperature, and here it's 1 over temperature. And then how order parameter depends on temperature, and there is a square root singularity here. This is absolutely typical. This is the signature of those phase transitions. And Landau theory of phase transition. But also I can do the following. Look at this. That's another trick which we learned how to do. Let's imagine that what I do, I change my omega just a little bit. And I see how the theta naught is changing. Okay, that makes sense? What it means practically is that I need to take the derivative. What the derivative means? This is function of omega, right? This is function of omega. I change an omega a little bit, and I see how my function is changing. That's exactly what derivative means. But then what I have, when omega is less than omega critical, I have theta naught equals 0 independent of omega. So that will be 0 here, that derivative, right? But here I need to, but in this region, when omega becomes larger than omega critical, I need to differentiate the square root. And the derivative of the square root is 1 over square root. Right?
Yeah.
Mm-hmm.
So it means that the response of my theta naught to small changes of frequency is actually divergent here. It goes to infinity. Right? Yeah. It's a derivative. So it means that the system becomes very, very sensitive. In this case, in this place, the system becomes very sensitive to the parameters of the problem. A small change of the parameter changes the theta naught a lot. Right?
Yeah.
But that exactly means that it will be very sensitive to any noise. So that's why that point where the beta is either to the left or to the right is so much depends on noise. Although the noise is very, very small, it can be very, very small. But the system responds very enthusiastically to anything exactly at this point. When we cross that critical omega, the critical frequency. So the system, although the noise is small, but that noise must be multiplied by the divergent number, the response function. Does it make sense?
Yes.
Yeah.
So that's why even small noise has a huge role in the outcome of the system. And that's why we cannot predict where it goes to the left, to the right, because we cannot predict a noise, right? All right. Any questions?
No.
Did it all make sense?
Mostly.
Yeah. All right. So I really suggest you to read that lecture notes, especially if you want to solve the homework problems. Because all the calculations are there. And well, thank you for coming and to my office, and see you on Wednesday.
Thank you. See you next time.
Thank you.